so now we're going to delve a lot more deep into rational and irrational numbers and what the proofs look like. And you'll notice a lot of the times, because irrationality is kind of difficult to prove, when you're encountering it, you're often going to be doing a proof by contradiction. So what are we doing today? Well, today we're going to ask ourselves, is the product of a rational and irrational number irrational? So what this means is, if I have 2 times pi equal x, is x irrational, right? Because 2 is rational, but pi is irrational. How do we write this proof? Well, we need to remind ourselves what the definition of irrational is, or rational. A rational number is an integer, for example, x, such that x is equal to m over n, where m, n are integers, n is not equal to 0, and no common factors between m and n. These are the 3 conditions a number has to meet in order to be considered rational. So we're going to do this by a proof of contradiction. We're going to instead say, well, let a rational and irrational number, the product of those two, be rational, right? So what does this mean? This means that we can say in our proof, let's suppose x and y are integers, and q is irrational, right? Then we're going to say x times q should equal y, right? Okay, that's what we're asking. Rational multiplied by irrational, is that going to equal irrational? Well, what can we do here? Maybe we can try, if you want to prove irrationality, you're going to want to find something that doesn't make sense. Well, maybe if we can rearrange this to say q must then be y over x. I see. Okay. I have the logic down. I just need to add a few more conditions in my initial statement. So let's just say, suppose x and y are rational. It wouldn't have made sense for me to say they're integers, because that wouldn't include the fraction rational numbers. So suppose x and y are rational and q is irrational. Okay. Then we can say x times q is equal to y. Or I guess we have to add another statement. We suppose x multiplied by q is y. Then what we can say is x, or we can rearrange this, right, with the way multiplication works. Q must then be equal to x over y, right? No, okay. The thing I'm struggling with is the x as the denominator. I keep forgetting. Let's do this case by case. Case 1, we're going to say x is equal to 0, then x multiplied by q is equal to y, which means 0 times q is equal to 0. So in this case, our proof by contradiction is going to be true. We're saying that if x is 0, then this is in fact true. 0 times anything is going to be 0, and 0 is an irrational number. Okay, but let's look at the second case, because we're asking a general question, right? Case 2, x is not equal to 0. Well, if x is not equal to 0, then q is equal to x over y, where x comma y, because they're both rational numbers, can be simplified Let me correct this again. X over y can be simplified so that x over y is going to equal to a over b for some... Okay. Keep making mistakes, but that's okay, because when you're writing proofs, you figure out what the proof should be as you write it. So here's what I'm going to say. We're going to say x cannot be 0. Let x be m over n and y be a over b for some m, n, a, b that are integers. Next, q would be y over x, okay, which is going to equal to y is a, b, and then x, 1 over x is n, m, where, oh gosh, we're gonna have to say, well, y can't be 0. We have to recognize that if y is 0, then q or x have to be 0. Q can't be 0 because 0 is a rational number, so that's out of the picture. So the only possibility for y to be 0 is if x is 0, and in our case, x cannot be 0. So we don't have to worry about y being 0. So we can just say where a n comma b m are integers and bm is not equal to 0. That's why I was just saying that, like, looking at this denominator, I need to make sure it's not 0, but it can't be 0 because x isn't 0 and y isn't 0. Great. And we can potentially simplify an over bm so that if an and bm share common factors, they don't. Maybe there's a better way of writing that sentence, but I think you get the idea. Which contradicts, oh, better yet, which makes Q rational, right? Contradicting our, do we suppose it? Yeah, supposition. Okay, so in writing this proof, I realized that we can't define x and y as integers because rational numbers are not all integers. There's more than that. So we just say x and y are rational and q is irrational. Then I recognize that there's one case where this is true, and that's when x is equal to 0. So I split this up into two cases. X is equal to 0, then x times q times is equal to y, which means y is also equal to 0. Great. That's the only case where y can be 0 and x can be 0, or and kind of both. It's an or and an and at the same time. In the second case where x cannot be 0, we can define x and y to be some fraction of integers for some mnab that are integers, which means that then when you rearrange for q, q is equal to y over x, which is equal to an over bn, which means q can be written as an integer divided by another integer. And then because the denominator cannot be 0, because in our case x is not equal to 0, which means y cannot be equal to 0, and we can say that we can obviously simplify an and bm so they don't share common factors if they already don't, so we can fix that, which means that q is rational, which contradicts our supposition, because if you notice, we're saying q is irrational, but we first said q is irrational. And these two statements can't be true, and we just proved that if x times q is equal to y, it must be that q is rational when x is not equal to 0. So what this means is our original statement is the product of a rational and irrational number irrational. Well, it must be, because when it's rational, it doesn't make sense. It's only true when x is equal to 0, or when the rational number is equal to 0. So yes, we can say which means the product of a rational and irrational is irrational. Again, because when it's rational, q has to be rational. So, awesome. We've just proven this by contradiction, so I hope this kind of made sense. Proving is very difficult, and like I said, as you write your proof, you usually figure out what statements you have to make. Like here I figured out, oh, I needed to split this into two cases because I thought of a case as I was writing it. Awesome. So there we go.